This is a training module for Atmel AT91SAM7S 32-bit ARM-based microcontrollers. Welcome to the training module on the AT91SAM 32-bit ARM-based microcontrollers. In the following presentation, you will learn about basic features of the AT91SAM7S, the peripherals like ADC, USART, USB, timer, pulse width modulation, etc. Atmel's AT91SAM7S is a series of low pin count flash microcontrollers based on the 32-bit ARM RISC processor. It features a high-speed flash and an SRAM, a large set of peripherals including a USB 2.0 device, and a complete set of system functions, minimizing the number of external components. The device is an ideal migration path for 8-bit microcontroller users looking for additional performance and extended memory. It includes a reset controller capable of managing the power-on sequence of the microcontroller and the complete system. Correct device operation can be monitored by a built-in brownout detector and a watchdog running off an integrated RC oscillator. The AT91SAM7S series is based on the ARM7TDMI processing core. The embedded flash memory can be programmed in-system via the JTAG ICE interface or via a parallel interface on a production programmer prior to mounting. Built-in lock bits and a security bit protect the firmware from accidental overwrite and preserves its confidentiality. The AT91SAM7S series system controller includes a reset controller capable of managing the power-on sequence of the microcontroller and the complete system. The AT91SAM7S series are a general-purpose microcontrollers. Their integrated USB device port makes them ideal devices for peripheral applications requiring connectivity to a PC or a cellular phone. The ARM7TDMI core executes both the 32-bit ARM and 16-bit thumb instruction sets, allowing the user to trade off between high performance and high code density. The ARM7TDMI processor implements von Neumann architecture using a three-stage pipeline consisting of fetch, decode, and execute stages. ARM7TDMI supports byte, 8-bit, half-word 16-bit, and word 32-bit data types. Words must be aligned to 4-byte boundaries and half-words to 2-byte boundaries. The memory controller MC manages the ASB bus and controls access requested by the masters. Typically the ARM7TDMI processor and the Peripheral DMA controller. It features a simple bus arbiter, an address decoder, an abort status, a misalignment detector, and an embedded flash controller. The memory controller has a simple hardwired priority bus arbiter that gives the control of the bus to one of the two masters. The Peripheral DMA controller has the highest priority. The ARM processor has the lowest one. The reset controller, RSTC, based on power-on reset cells, handles all the resets of the system without any external components. It reports which reset occurred last. The reset controller also drives independently or simultaneously the external reset and the peripheral and processor resets. A brownout detection is also available to prevent the processor from falling into an unpredictable state. The reset controller is made up of an NRST manager, brownout manager, a startup counter, and a reset state manager. It runs at slow clock and generates the following reset signals. These reset signals are asserted by the reset controller, either on external events or on a software action. The reset state manager controls the generation of reset signals and provides a signal to the NRST manager when an assertion of the NRST pin is required. The real-time timer is built around a 32-bit counter and used to count elapsed seconds. It generates a periodic interrupt and triggers an alarm on a programmed value. The real-time timer is used to count elapsed seconds. It is built around a 32-bit counter fed by a slow clock divided by a programmable 16-bit value. The value can be programmed in the field RT/PRES of the real-time mode register RTT_MR. The programming of RT/PRES to 1 or 2 is possible, but may result in losing status events because the status register is cleared by 2 slow clock cycles after read. Thus, if the RTT is configured to trigger an interrupt, the interrupt occurs during 2 slow clock cycles after reading RTT_SR. The periodic interval timer, PIT, provides the operating system scheduler interrupt. It is designed to offer maximum accuracy and efficient management, even for systems with long response times. The periodic interval timer aims at providing periodic interrupts for use by operating systems. The PIT provides a programmable overflow counter and a reset on read feature. It is built around 2 counters, a 20-bit CPIV counter and a 12-bit PICNT counter. Both counters work at master clock divided by 16. The first 20-bit CPIV counter increments from 0 up to a programmable overflow value set in the field PIV of the mode register PIT_MR. The boot program integrates different programs permitting download and/or upload into the different memories of the product. First, it initializes the debug unit serial port, DBGU, and the USB device port, SAM-BA. Boot is then executed. It waits for transactions either on the USB device or on the DBGU serial port. The USB device port, UDP, is compliant with the Universal Serial Bus USB version 2.0 full-speed device specification. Each endpoint can be configured in one of several USB transfer types. It can be associated with 1 or 2 banks of a dual-port RAM used to store the current data payload. If 2 banks are used, one DPR bank is read or written by the processor, while the other is read or written by the USB device peripheral. This feature is mandatory for isosynchronous endpoints. Thus, the device maintains the maximum bandwidth 1 megabytes per second by working with endpoints with 2 banks of DPR. The PWM macrocell controls several channels independently. Each channel controls 1 square output waveform. Characteristics of the output waveform, such as period, duty cycle, and polarity, are configurable through the user interface. Each channel selects and uses one of the clocks provided by the clock generator. The clock generator provides several clocks resulting from the division of the pulse width modulated macrocell master clock. All PWM macrocell accesses are made through the APB mapped registers. Channels can be synchronized to generate non-overlapped waveforms. All channels integrate a double buffering system in order to prevent an unexpected output waveform while modifying the period or the duty cycle. The AT91SAM7S series microcontrollers feature a number of complementary debug and test capabilities. A common JTAG ICE port is used for standard debugging functions, such as downloading code and single-stepping through programs. The debug unit provides a 2-pin UART that can be used to upload an application into internal SRAM. It manages the interrupt handling of the internal COMMTX and COMMRX signals that trace the activity of the debug communication channel. A set of dedicated debug and test input-output pins gives direct access to these capabilities from a PC-based test environment. The Universal Synchronous Asynchronous Receiver Transceiver, USART, provides one full duplex universal synchronous asynchronous serial link. Data frame format is widely programmable to support a maximum of standards. The receiver implements parity error, framing error, and overrun error detection. The receiver timeout enables handling of variable length frames, and the transmitter time guard facilitates communication with slow remote devices. Multi-drop communications are also supported through address bit handling in reception and transmission. The USART features 3 test modes: remote loopback, local loopback, and automatic echo. The USART supports specific operating modes, providing interfaces on RS-485 buses. The Serial Peripheral Interface (SPI) circuit is a synchronous serial data link that provides communication with external devices in master or slave mode. It also enables communication between processors if an external processor is connected to the system. The Serial Peripheral Interface is essentially a shift register that serially transmits data bits to other SPIs. During a data transfer, one SPI system acts as the master, which controls the data flow, while the other devices act as slaves, which have data shifted into and out by the master. Different CPUs can take turns being the master. The ADC is based on a successive approximation register, SAR, 10-bit analog to digital converter. It also integrates an 8-to-1 analog multiplexer, making possible the analog to digital conversions of 8 analog lines. The conversions extend from 0 volts to ADV ref. The ADC supports an 8-bit or 10-bit resolution mode, and conversion results are reported to a common register for all channels, as well as in a channel-dedicated register. Software trigger and external trigger on rising edge of the ADT RG pin or internal triggers from timer counter output are configurable. The ADC also integrates a sleep mode and a conversion sequencer and connects with a PDC channel. These features reduce both power consumption and processor intervention. The ADC uses the ADC clock to perform conversions. Converting a single analog value to a 10-bit digital data requires sample and hold clock cycles as defined in the field SHTIM of the ADC mode register and 10 ADC clock cycles. The ADC clock frequency is selected in the prescale field of the mode register ADC_MR.